In the previous video, I mentioned the position of equilibrium in terms of whether there was a higher concentration of products or reactants when equilibrium was established. So in this situation here, we can see that at equilibrium, we've got a higher concentration of products, which means that the reaction has a higher yield. We're further to the right over here. Whereas in this situation here, we can see at equilibrium, we've got a higher concentration of reactants, which means that the reaction is further to the left, or we've got more reactants, which will mean we've got a lower yield of products. So the position of equilibrium essentially refers to your ratio of reactants and products, concentrations at equilibrium. And it gives you an idea of the extent of the reaction, how far it is towards the production of products. One way that we can look at the extent of a reaction or the position of equilibrium is using the equilibrium constant, which compares the concentration of reactants and products at equilibrium. So what this represents is, if we have a look at this expression down here, we've got reactants A and B reacting to form products C and D. So we've got the concentration of C raised to the power of the coefficient from the equation times by the concentration of product D raised to the power of the coefficient in the equation. And that's divided by the concentration of reactant A to the power of its coefficient in the equation times by the concentration of reactant B to the power of its coefficient in the equation. So essentially we have something that looks at the concentration of the products over the concentration of the reactants. If we think about this as a fraction for the moment, we can see that the larger this number on the bottom here is, the smaller the overall number will be. So essentially what that means is the larger the concentration of the reactants, the smaller our equilibrium constant will be. So it's in that way that the equilibrium constant can give us an indication of the extent of the reaction. So if something has a large equilibrium constant, so in terms of large, we generally say larger than 10, greater than 10, that's going to indicate a high product yield. And that's because during equilibrium, the concentration of the products is going to be significantly higher than the concentration of the reactants. And we would refer to the reaction as being further to the right. So it's further in the direction of the products. If, however, we have a small equilibrium constant, that's going to indicate a low product yield. So what that means, a low yield, it means we don't have a lot of products. And so in this situation, a small equilibrium constant tells us that at equilibrium, the concentration of our reactants is greater than the concentration of our products. So we would say in that case that the reaction is to the left. So let's now have a look at how you might calculate the equilibrium constant. And to do that, we'll look at the conversion of sulfur dioxide into sulfur trioxide. Okay, so in this situation, we are told at a temperature of 727 degrees Celsius, the equilibrium concentrations of the reactants and products are as given here. The first thing you want to do is write the equilibrium expression. So remember, we're going to have our product, so the concentration of raised to the power of the coefficient in the equation. So because the SO3 or the sulfur trioxide has a coefficient of 2, in the equilibrium expression, the concentration of sulfur trioxide needs to be squared. Now that's going to be over the concentration of the first reactant, so sulfur dioxide, raised to the power of 2, because it's got a coefficient of 2 in the equation, times by concentration of our other reactant, which is oxygen. Now this only has a coefficient of 1 in the equation, so it's only to the power of 1. So that's the equilibrium constant expression. So if you're ever asked for the expression, it's just asking for that part where you've substituted in the formulas and you haven't yet put in the values for the calculation. So once you've written the expression, the next step is to substitute in the concentration values. Once you've done that, your next step is to do the calculation. And we end up with an equilibrium constant of 174. So we can tell by that, that's a relatively large equilibrium constant. So that means that the reaction is towards the right. We're going to have a relatively high yield of our product. So we're going to have greater amount of product than reactants at equilibrium. So sometimes you might be asked to use the equilibrium constant at a given temperature as well as some concentration information to find some other concentration information. So that's the concentrations initially or the concentrations at equilibrium. So for the reaction between sulfur dioxide and oxygen to produce sulfur trioxide at 727 degrees Celsius, we just established that the equilibrium constant using the equilibrium concentrations given was 174. So sometimes you might be asked to then find the initial concentration of something. So in this case, if we were told there was initially no product, so there was no sulfur trioxide to start with, what were the initial concentrations of sulfur dioxide and oxygen? Now the way that we can do that is by establishing an ICE table. So to do that, we just need to write the letters ICE. The I stands for initial, the C stands for change, and the E stands for equilibrium. And what we use this to do is look at the concentration in each of those situations. So the initial concentration, the equilibrium concentration, and the change that has occurred between the initial and the equilibrium concentrations. So we've set up the start of our ICE table, so ICE down the side there. The next thing we want to do is write the equation for the reaction. And that's going to act in two ways. One, it's going to tell us the reactants and products that we're considering. And secondly, the mole ratio here. So the coefficients of our reactants and our products are going to be very useful. So once we've done that, we need to populate the table with the information that we have been given in the question. So in this situation, we were told the equilibrium concentration of all three substances. So the initial question told us that the equilibrium concentration of sulfur dioxide was 0.0223. The equilibrium concentration of oxygen was 0.0150, and the equilibrium concentration of sulfur trioxide was 0.0360. Now we've also been told that there was no sulfur trioxide initially, so that means our initial concentration was 0. So at this point, we've put in all of the information that we know. So if we have a look at this, if we know that we had no sulfur trioxide initially and we've got 0.036 moles per litre at equilibrium, we can calculate the change. Okay, so obviously going from 0 up to 0.036, we've seen an increase in 0.0360 moles per litre. So our change was an increase by this amount. Now this is where our mole ratio comes in. So we can use the mole ratios from the equation up here to calculate, well, if this many moles of sulfur trioxide have been produced, how many moles of our reactants must have been used. So if we have a look at the ratio between sulfur dioxide and sulfur trioxide, we can see that it is a 1-to-1 ratio. So that means that if this many moles, 0.0360 moles of sulfur trioxide were produced, then 0.0360 moles of sulfur dioxide must have been consumed. Now, because the concentration in this case has decreased, we put a little negative sign. And now if we compare the mole ratio of oxygen to our sulfur trioxide, we'll see that it's a 1-to-2 ratio. So half the number of moles of oxygen. So if we half this number here and we get 0.0180 moles of oxygen would have been consumed. So lastly, if we know what our equilibrium concentration is and we know what our change is, we can calculate our initial concentrations. So we can see going from our initial to our equilibrium, the change, we've gone down. So going back from our equilibrium to our initial, we want to add this number on here. So we do our 0.0223 plus 0.0360, and we'll end up with 0.0583. Same over here, our 0.0150, add 0.0180, and we end up with 0.0330. So now we've calculated our initial concentrations of the sulfur dioxide and oxygen.